Imagine a world where the familiar rules of physics dissolve, a realm where particles behave like waves and the impossible becomes possible. This is the captivating world of quantum mechanics, a branch of physics that governs the behavior of matter at the atomic and subatomic levels. It is a world of perplexing paradoxes and mind-boggling phenomena that challenge our classical intuition. The journey into the quantum realm begins with the understanding that the laws governing the macroscopic world, the world we experience with our senses, break down at the atomic scale. Here, particles like electrons and photons exhibit bizarre behaviors, defying our everyday experiences. They can exist in multiple states at once, tunnel through impenetrable barriers, and even communicate instantaneously across vast distances. The implications of quantum mechanics extend far beyond the realm of theoretical physics. It underpins our understanding of chemistry, material science, and even biology. It has led to groundbreaking technologies like lasers, transistors, and magnetic resonance imaging, revolutionizing our lives in countless ways. This essay will delve into the heart of quantum mechanics, exploring its key concepts and their profound implications. From the enigmatic wave-particle duality to the spooky action of entanglement, we will unravel the mysteries of the quantum world and explore how it shapes our understanding of the universe and our place within it. One of the most fundamental and perplexing concepts in quantum mechanics is wave-particle duality. This principle, seemingly contradictory to our everyday experience, states that particles can exhibit both wave-like and particle-like behavior. Imagine a beam of light. In some experiments, it behaves like a wave, diffracting through narrow slits and creating interference patterns. Yet in other experiments, light behaves like a stream of particles called photons, each carrying a discrete amount of energy. This dual nature is not limited to light. Electrons, the fundamental particles that orbit the nucleus of an atom, also exhibit wave-particle duality. In electron microscopes, for example, beams of electrons are used to image objects far too small to be seen with visible light. This is possible because electrons, like light waves, can diffract and interfere, allowing us to create highly magnified images. But how can something be both a wave and a particle simultaneously? The answer lies in the heart of quantum mechanics. The behavior of quantum entities is governed by a wave function, a mathematical description that encapsulates all the information about the particle's state. This wave function doesn't describe the particle's position or momentum directly, but rather provides a set of probabilities for finding the particle in a particular state. When we measure a quantum entity like an electron, we force it to collapse from its wave-like superposition into a definite particle-like state. This act of measurement fundamentally alters the system, highlighting the active role of the observer in quantum mechanics. Wave-particle duality underscores the probabilistic nature of the quantum world, where certainty gives way to a tapestry of possibilities. In the quantum realm, the familiar notion of a particle existing in a single well-defined state crumbles. Instead, particles can exist in a superposition of states, a concept that defies our classical intuition. Imagine a coin spinning in the air, neither heads nor tails but a blurry combination of both. This analogy, though imperfect, hints at the perplexing nature of superposition. A quantum entity in superposition exists in a combination of all possible states simultaneously. It is not that the particle is rapidly switching between states, rather, it exists in all states at once. A concept that challenges our everyday understanding of reality. Only when we attempt to measure its state does the superposition collapse, and the particle chooses one definite state. To illustrate this concept, consider the famous thought experiment known as Schrödinger's cat. A cat is placed in a box with a device that has a 50% chance of releasing a lethal poison. Until the box is opened, the cat exists in a superposition of being both alive and dead. It is the act of observation, of opening the box, that forces the cat's state to collapse into one of the two possibilities. Superposition is not merely a theoretical curiosity. It has profound implications for quantum computing, where quantum bits or qubits can exist in a superposition of 0 and 1 states, allowing for exponentially faster computations compared to classical computers. Entanglement, one of the most bizarre and intriguing phenomena in quantum mechanics, occurs when two or more particles become correlated, even when separated by vast distances. These entangled particles share a special connection, a bond that transcends space. Imagine two coins flipped simultaneously, always landing on the same side, even if one coin is on Earth and the other on Mars. When two entangled particles are measured, the outcome of one measurement instantly determines the outcome of the other, regardless of the distance between them. This spooky action at a distance, as Einstein famously called it, seems to violate the principle of locality, which states that an object can only be influenced by its immediate surroundings. The strangeness of entanglement lies in the fact that the act of measuring one entangled particle seems to instantaneously influence the state of the other, even if they are light years apart. This has led to much debate and speculation about the nature of reality and the limits of our understanding of the universe. Despite its bizarre nature, entanglement is a very real phenomenon with practical applications. It forms the bedrock of quantum cryptography, where entangled particles are used to create unbreakable codes. It also plays a crucial role in quantum teleportation, where the quantum state of one particle can be transferred to another distant particle. Imagine a ball rolling up a hill. In the classical world, if the ball doesn't have enough energy to reach the top, it will always roll back down. But in the quantum realm, there's a chance the ball could tunnel straight through the hill, appearing on the other side, as if by magic. This is quantum tunneling. Quantum tunneling arises from the wave-like nature of particles. Just as a sound wave can pass through a wall, albeit at a reduced intensity, a particle's wave function can extend beyond a potential barrier, even if the particle doesn't have enough energy to overcome it classically. This means there's a non-zero probability of finding the particle on the other side of the barrier, as if it had tunneled through. This phenomenon, as mind-bending as it seems, is not science fiction. It's the reason our sun shines. The immense pressure and heat within the sun's core are not sufficient for classical fusion reactions to occur. However, thanks to quantum tunneling, protons can overcome their mutual repulsion and fuse, releasing the energy that sustains life on Earth. Quantum tunneling also plays a crucial role in electronics. It's the mechanism behind tunnel diodes, which are used in high-frequency circuits, and scanning tunneling microscopes, which allow us to image surfaces at the atomic level. Section 6. Quantum applications, from lasers to medical marvels. Quantum mechanics, despite its reputation for being abstract and esoteric, has led to a wealth of practical applications that have revolutionized our world. From the lasers that read our Blu-rays to the medical marvels of MRI scans, quantum mechanics underpins many technologies we rely on daily. Lasers, for instance, exploit the quantum property of stimulated emission, where photons interact with excited atoms, causing them to release identical photons, resulting in a highly focused beam of light with remarkable properties. Lasers are ubiquitous, used in telecommunications, barcode scanners, laser surgery, and countless other applications. Magnetic resonance imaging, or MRI, is another medical marvel that relies on quantum mechanics. MRI exploits the magnetic properties of atomic nuclei to produce detailed images of the inside of the body. By placing a patient in a strong magnetic field and applying radio waves, doctors can visualize organs, tissues, and even blood flow, enabling earlier and more accurate diagnoses. Beyond lasers and MRI, quantum mechanics underpins the development of semiconductors, transistors, and integrated circuits, the building blocks of modern electronics. Our smartphones, computers, and the internet all owe their existence to the principles of quantum mechanics. Section 7. Quantum computing. The dawn of a new era. Quantum computing, still in its infancy, holds the promise of revolutionizing fields like medicine, materials science, and artificial intelligence by harnessing the power of superposition and entanglement. Unlike classical computers, which store information as bits representing 0 or 1, quantum computers use qubits. Qubits, thanks to superposition, can exist in a combination of 0 and 1 states simultaneously, allowing quantum computers to perform computations on multiple possible values at once. This massive parallelism gives quantum computers the potential to outperform classical computers for specific tasks, such as factoring large numbers or simulating complex molecules. Imagine designing new drugs and materials with unprecedented speed and precision, or developing artificial intelligence with human-like cognitive abilities. These are just a few potential applications of quantum computing. While still in its early stages, quantum computing has the potential to usher in a new era of technological advancements. Section 8. The unexplored landscape of quantum biology. Quantum biology is an emerging field that seeks to understand if and how quantum mechanics plays a role in biological processes. While quantum effects are often associated with the microscopic world, recent research suggests that they might be at play in living organisms, influencing processes like photosynthesis, enzyme catalysis, and even avian navigation. For example, there's evidence that birds use a magnetic compass based on quantum entanglement to navigate during migration. Photosynthesis, the process by which plants convert sunlight into energy, also seems to rely on quantum coherence, where energy is transferred efficiently through a network of molecules. The exploration of quantum biology is still in its early stages, but the implications are profound. Unraveling the quantum secrets of life could revolutionize our understanding of biology, leading to new medical treatments and a deeper appreciation for the interconnectedness of the quantum world and the living world. Section 9. Conclusion: Quantum Mechanics, a journey into the unknown. Quantum mechanics, with its mind-bending concepts and counterintuitive predictions, has fundamentally altered our understanding of the universe. It has unveiled a realm where the familiar rules of classical physics break down, replaced by a world of probabilities, uncertainties, and spooky connections. From the wave-particle duality to the enigmatic entanglement, quantum mechanics challenges our classical intuition at every turn. Yet it is precisely these perplexing aspects that make it so captivating and hold the key to unlocking new technological frontiers. As we delve deeper into the quantum realm, we continue to uncover new mysteries and possibilities. Quantum computing, quantum biology, and countless other fields are poised for revolutionary advancements, driven by our growing understanding of this strange and wonderful world. The journey into the quantum realm is far from over. It is a journey that promises to challenge our assumptions, expand our horizons, and lead us to a deeper understanding of the universe and our place within it.